All right, so midterm will be on Thursday in here. It'll take, you'll have an hour and 15 minutes to take it. Um, it hopefully won't be a time sensitive thing. I try not to make my exams, um, I guess, time sensitive. So if you feel like it's a time crunch for the exam, then you probably don't know the stuff as well as you should. So use that as your, wake up call, I guess. Remember that my policy for exams is if you do better on the final than you do on the midterm, I'll replace your midterm grade with whatever you got on the final. So you get a get out of jail free card, but it doesn't work the other way around. The hope is that it's relatively low stress and more for a wake up call for some of you than anything else. Because even if you do well on the midterm, let's say you get a 91 on the midterm or something like that, there's still room to improve that grade with your final, right? So, it's not a one and done type thing. Use it to kind of give you a measuring stick of where you sit in the class. All right, any questions on the general format of the exam before I start getting into the content that I'm likely to focus on? Okay. So the exam is going to have a couple of, let me give you a little general format. The exam will probably have 10 questions on it. There will probably be a couple of assembly programming questions. There likely will be some, maybe
you tell us, I want you
to write something that does something. Yeah. Then there might be one or two questions where I give you some assembly and say, what does this do? Something like that. Being able to read assembly and kind of understand the register stuff. I doubt very much more than 4 questions will have to do with assembly directly. Okay, because even though that's what we've been doing recently, that's not what we've done the whole semester, right? So as we go through this, I'll hopefully give you some talking points for the rest. And then Then the second half of the semester, we're gonna kind of pause assembly a little bit. I have a couple of loose ends to tie up there, but then I want to start getting into circuit design, and we're going to be talking about gates and things like that, and then trying to pull all that together near the end to how those two kind of fit together. Go ahead.
Are there any high-level programming questions?
Well, I guess maybe. Let's flip through this. I haven't written it yet, so the answer is maybe. So what you're seeing, and this is actually, there's 2 reasons. One's laziness, but actually I think beneficial to you, because as I'm going through these slides, you're getting my real-time reaction to how important I think a topic is. This is exactly what I would do for the exam. Is I just flip through the slides and see what. Otherwise, what ends up happening is sometimes I'll ask a question that I thought I covered, but I didn't. Didn't that happen last semester? I've been in 200? There was some question I asked that everybody missed. And in my mind, I covered it, but I totally didn't. I still gave them zeros, but I mean... But yeah, that especially when you teach so many classes that have similar topics, then you get confused on what you talked about in what class. That's why I go with this. Yeah, but the problem is sometimes I write the exams, I voice dictate them while I'm driving. So, go ahead. You won't have to memorize any of it. If I want you to use DOS API stuff, I would probably just put a picture up there, or I would put it up on the board or something like that. You don't have to memorize any of the calls, like 9H or anything like that.
Well, then how are we supposed to do the assembly program?
I would give you anything you needed to do.
Okay.
So you should be able to read that DOS API instructions, but you don't have to memorize it. If I need you to use it for the exam, I'd give it to you. Yeah, I mean, I'm not a fan of memorization stuff. I want you to show that you understand something, but in the real world, I mean, it's not like somebody's going to lock you in a room and say, okay, write DOS API stuff, right? With just no documentation or anything, just go. So I want to see what your competence is, not what you memorized. Make sense? And if I forget to give you something that I intended to give you during the exam, just come up and I'll just tell you and tell the rest of the class during it. My intention isn't memorization stuff.
Everybody else is good, but I'll be screwed.
Yeah, I think I'll cover it. Anything you need will be on there. Yeah. Otherwise, just email me or write a note or something, and I'll just make something up.
Run upstairs.
Well, no, just make something up. If there's a system call that you're supposed to use that I didn't give you, just make up a system call and just put a question mark next to it. I'll just pretend like you had it. It'll be fine. I intend to give you everything you'll need, or it won't apply. This won't be a thing. Okay, so we started off talking about the CPU. There'll definitely be at least one question dealing with the CPU in terms of its nature. So this idea that it's a collection of circuits, and we're going to talk about the nature of those circuits in much more detail the second half of the semester. But a collection of magic tricks, the idea of registers, idea of memory that sits on the CPU. So I can certainly see a question about the general use of registers. I probably would not ask a question like, what's the intended use of AX versus BX versus CX, because they're general use type things. They have their, it's almost like the DOS API gives them some semantic meaning, but in general, I want to know kind of the advantage of registers versus cache, how memory is maybe used relative to these magic tricks, that kind of stuff. So as we keep going through here, I'll talk about this. So let's see. So, for example, when we're talking about hardware registers, the thing that should come to mind is the idea that they're really, 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 really fast, really, 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 really expensive per, let's just say, byte to keep it down to some sort of minimal level. But they're fast and they're very close to the CPU, so that's where we want to work out of those guys a majority of the time when we need to do calculations. All right, as we get farther and farther away from the CPU, that's when we have slower and slower memory, kind of on the extreme side if we're still dealing with memory, our system RAM, which we think of, like the 8 gigabytes of RAM in our machine. We think of that as being fast relative to us, but in the range of memory, it's very slow compared to a register. Okay? So we want to think about that distance traveled that has some performance implications, and we can connect that to what we've been dealing with in the assembly world, where we have a direct register versus a memory address, and or versus memory. And one of the things we've noticed, like the move command, doesn't allow you to move something from one variable into another variable, because that's considered to be very inefficient. So we move a variable into a register, and then a register into a different variable. It's a two-step process. Okay, so variables are actually stored inside of system memory, system RAM, and that's considered slow by CPU performance standards. It'll be a bottleneck. All right. So kind of the discussion dealing with our Intel architecture, which is an expanded instruction set, or doesn't attempt to be a reduced instruction set, versus a reduced instruction set idea. So, for example, if I had asked you on an exam, or if I do ask you on an exam, what's the idea of a reduced instruction set, and what's the benefits and weaknesses of it? What might you say? What's the purpose of reduced instruction set? Go ahead.
It has like the fewest possible tools to solve any given problem.
Okay.
I guess the point is to avoid having to provide all those tools and avoiding heat.
Okay.
Energy.
So less magic tricks to solve the problem. Therefore, each magic trick might be larger potentially, because you're trying to capture all the little tools that you need to solve general purpose problems in less magic tricks. But the hope is then, because they're not disproportionately larger, that you actually do save space on the CPU, therefore reduce heat. It's kind of the idea. The less magic tricks you have to implement, the less heat you have, all that kind of jazz. Now, they did sort of die off, right? So where did reduced instruction set processors die on the desktop world for us as consumers? We had two competitors. So think back to PC versus Mac. For a long time, Macintosh computers used what kind of processor? PowerPC chip, which was an IBM processor based on reduced instruction set. Okay, and that fell to the wayside. Part of it was Intel clearly was kind of the winner, and there was a movement towards compatibility, right? But the other side of it is that they were hard to produce. IBM was having trouble producing those guys, and part of it was almost a backfire because of the heat. They were running too hot. So the one thing they were trying not to do happened. Now, with that in mind, is reduced instruction set dead? Yeah, it's making a comeback today, right? So all these ARM processors are reduced instruction set processors. Why do you think it's successfully making a comeback in mobile devices? So less magic tricks to power means maybe better battery life. That's one thing.
So it was like the Raspberry Pis and Arduinos. Would it save money to do that?
I don't know if that comes down directly to reduced instruction set versus expanded instruction set, but possibly. I mean, because they're maybe easier to mass produce today. We have better technology for making them today. Yeah.
Would the chips be smaller because there's less of it on them?
Could be. They could be smaller. Part of that's because less of the chip needs to be dedicated to heat dissipation. So that's certainly a reality. The battery is certainly a reality. Now, if we go back to capturing that general purposeness of it, I mean, on any of these general purpose processors, we're trying to give enough magic tricks to solve the general classification of problems. Might we assume that in the mobile world, that general classification of problems might be smaller than it is on the desktop world? It's kind of always expanding, right? Because how long is it until we come home, drop this into some dock, and this is now our computer? I mean, we do that with our laptops, right? You come home, you plug it in, and that's your computer. It's just we're not running off battery power now. And I think there's some newer laptops that actually the Surfaces, right? The Surface Pros, there's a lot of hardware in the keyboard, is my understanding. So when you take the keyboard off and it's a tablet, it's a significantly lower powered device. Once you hook the keyboard into it, it becomes more of a mainstream machine, right? And so that's kind of almost our growing pains of where we're going. So it's not far-fetched to say that this guy becomes our computer sooner rather than later, where we come home and it's a mobile operating system when we're on the go. You drop it in and all of a sudden this becomes your computing power. Maybe it's hooked into some hard drive or something that actually is running a desktop operating system, but this is your computing power in your graphics card or something like that for your desktop computer. So the idea that the general purposeness of your mobile device is needs fewer options than our desktop devices is probably becoming less and less true every day. But it is probably one of the reasons why ARM processors did make sense for mobile and kind of made their comeback. But because our technology has gotten better in producing them and we've had more years of experience in coming up with what is that reduced instruction set, timing is also there. I don't think RISC was really a poor idea to begin with. It was more of maybe poor timing relative to where the competition was. So RISC is definitely coming back now. On an exam, I might ask you to kind of discuss the pros and cons of each, because there clearly isn't a right answer, right? I'm not going to ask you which is better and then mark you wrong if you choose the wrong option. I want to see your argument. So there could be a question, very likely will be a question dealing with benefits of reduced instruction set versus an expanded instruction set, pros and cons of that, your opinion of that. And if you can give me a well-formed opinion, then that shows me competence and that's points. Make sense? So I want you to understand the issue related to that. Let's see. I would put this in the 50-50 category. The process of an instruction getting onto the CPU and actually getting executed, that fetch, decode, execute, little 1, 2, 3 move. It was from one of your homework assignments from your book reading. If I need a filler question, that would be higher up on my list. I'll give you like 50%, 25%, 10% chance type thing. So I could see this as a filler question. Because to design the exam, I need to have a couple of programming questions that'll probably take up, half the exam time. And then you have to have basically 5 questions that are filler, that are important, but are, quick one-offs. Takes you 3 minutes to answer it and you move on with life. That way you have times for the other ones. So something like this might be what's the process of getting an instruction onto the CPU. I probably would not ask a question about AMD 64. It was an interesting in-class discussion, but it really gets covered by that whole discussion of RISC versus expanded instruction set, and really we just said it a few minutes ago, was timing, right? No, there's nothing wrong with the AMD 64 chips from a design perspective, just they were ahead of their time. We didn't have software to support it. So I'll say 10% chance that's on the exam. Low priority, I'll have to be really grasping for a question if I drop into AMD 64. Here's just basically the conversation we had before, Mac versus PC. Significantly higher probability of having some discussion, some question involving those early PowerPC versus Intel type things. So it'll be basically that discussion we just had a few minutes ago, something related to that. And probably one question there. The concept of firmware, I think certainly we'll call it 80% chance on the exam. So what's the purpose of firmware? Why do we have it? Okay, and so it's an intermediary, and why is that good? Why was it invented to begin with? Okay, tell me more. We're on shaky ground already, but
No, I can keep going. It's just going to be rambling.
Anybody want to give me a more coherent example of firmware? Or a reason for firmware? How is firmware? Oh, go ahead. Yeah, I mean, the idea is that when you build a hardware circuit for your our home entertainment systems or something like that, any sort of electronics we have at the house, these are hardware circuits. That's what makes them fast. But if there's a bug, so go back to your 150 class, what percent of programs have bugs in them? 99.999, whatever, blah, blah, blah. So if we're saying that hardware circuits are similar to programs, what percent of hardware circuits do you think have bugs in them? To some extent, I mean, you could have a pretty simple hardware circuit that does something pretty simple, but they're not error proof, right? They're prone to errors just like anything else. But those errors are harder to fix. If you have an error in your programming code, right, you just change a couple lines of code, recompile, and you're back in business. You have an error in your circuit, well, you got to start melting off solder or start from scratch, that kind of stuff. So where firmware comes in is they make parts of the circuit that need to be really, 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 really fast made of the actual hardware circuits. And then there's aspects of the logic that they can build into firmware, which is software that runs directly on the hardware. So almost think about this like the register argument, where hardware registers on our CPU are really fast, so using them is as good as we're going to get for quick storage. Firmware would be similar to that, where it's sitting very, very close to the hardware itself, but it's based in software. So we can upgrade the firmware and change or fix a potential problem with the hardware. Can't necessarily fix all the problems if your bug is involved in some of the soldered stuff as opposed to the software that runs on it. You have a problem, but the real purpose of firmware is to make hardware more easily upgradable or fixable. Make sense? But the trade-off will be performance, right? If we had everything as hard-coded hardware, well, hard-soldered, hard-soldered hardware, we're going to get our maximum performance, assuming it's a efficiently created circuit, but you then lose flexibility. So there's a trade-off in there. Okay, so 2's complement will definitely be on the exam. What's the purpose of 2's complement? Why does it exist? Okay, that's a true statement. It does allow us to subtract easier. How? How does that let us do that? Okay, so instead of subtraction, we can just do everything through addition. What about 2's complement lets us do that? What does 2's complement itself actually do? Yeah, it's a way of representing negative numbers. So it's a way of encoding a number as its negative version, as its signed version, right? Okay, it's a way of encoding a number as its signed version. So the second you say something's going to be 2's complement, you give up a bit, right? You give up a bit. So you're decreasing the maximum unsigned value size you can store because you're now utilizing one of those bits as part of the encoding process for the sign. Okay, it doesn't hold a positive or negative number directly. Why is that? Remember we talked about an alternative to 2's complement, and one of the alternatives was to just use that very first bit for sign. Anything with a 0 was positive, anything with a 1 was negative. What's wrong with that? What's the weakness of that that makes 2's complement, let's say, needed? You would do that anyways, wouldn't you? If you take an 8-bit number and turn it into 7 bits because you're guaranteeing the far left bit is sign.
You ended up with two different zeros.
Two different zeros. You had a positive and a negative 0. Yep. Not the, that's not the end of the world, but it is inefficient, right? So what does 2's complement guarantee? 2's complement gives us a single 0, gives us a unique space for each number, which then translates into, this is where that whole idea of something being negative 128 to positive 127, we get the extra value on the extra 1 on the negative side because we don't have 2 zeros. Make sense? So 2's complement allows us to accomplish that. So maybe a question involving why 2's complement exists, what problem does it solve, which is the problem of storing negative numbers, encoding negative numbers, the idea of supporting subtraction through addition. It solves the problem of having 2 zeros, representing 0 2 different ways. A positive and a negative 0 is a waste. And in some ways, a problem. Because how do you tell the difference between a 0 and a 0? A positive 0 and a negative 0. When you do logical things, it might not make sense. Because now you have 2 different things that mean the same thing. So that's more of rationale for 2's complement. Now, there could also be a question, I might even have both of these, dealing with actually doing a 2's complement. So how is 2's complement accomplished? If I give you a number, an 8-bit number or something like that, and I say convert this to its 2's complement, what would you do? Flip the bits and add a 1. Okay, that's converting it to 2's complement. Make sense? All right, so I could have you take a number and convert it to 2's complement. I could have you take 2 binary numbers and say subtract these from each other, which would then encourage you to turn them into its 2's complement, and then do the subtraction. Now, so playing devil's advocate here, let's say I give you 2 numbers, 2 8-bit binary numbers, and I say add these 2 numbers together. How would you go about doing that? What are some options for doing that on the exam? So this is almost test-taking strategy using for smart people. So what we just talked about was what? Convert the bottom number into its 2's complement and add. That's one way, right? Okay, so we can do addition. Now, what's another approach? Let's say you forgot how to do 2's complement, or you didn't have confidence in 2's complement to do that. What's another approach? Yeah, I mean that's the catch-all, right? How many of you think if I gave you 2 decimal numbers as to subtract these, that you could get that one right? I mean, we've been doing that for a while, right? Since like 3rd grade, 2nd grade, something like that. When did we do?
You would put a stipulation on using 2's complement?
I probably not. I would probably say subtract these 2 binary numbers. What you lose out on there, though, is the idea that, so if I gave you that and I wanted, because I'll give partial credit for work if you show your work. So if you got the wrong answer and I can't reverse engineer it and figure out where you went wrong, I can't give you partial credit. So if you convert them both into decimal and then subtract the decimal and then just put down the decimal version of your answer, but you mess up the decimal version of your answer, then I won't be able to, give you partial credit. But as long as you do your conversions right, then you can get it working. So you can turn 2 binary numbers into their decimal equivalent, do the subtraction, get your answer in decimal, then convert the decimal back to binary. That will get you points on an exam. Make sense? It will get you the answer on the exam. But the best way of doing it would be the 2's complement version of it. You could also actually do subtraction. I mean, binary does support subtraction. You can do subtraction with binary numbers. You don't need 2's complement to give you the convenience of addition. So you can just do straight subtraction. If I'm giving you a 4 or an 8-bit number, that shouldn't be too horrible. If I give you like a 64-bit number, which would just be funny. Just randomize zeros and ones. Make sure there's a 1 on the far left, where all of a sudden your calculator is just doing the whole scientific notation. Don't you hate that? It's no longer a real number. I could have fun with that. All right, so some tricks to use for the conversion questions is when in doubt, fall back on something you've been doing since 2nd grade. It's not necessarily the right way of doing it, but it's still showing that you have an understanding of binary to decimal, doing your mathy stuff and converting it back. I mean, it's a cop-out, but it's better than a 0 on the question, right? All right. All right, so then we kind of got into assembly language. Now, actually, before I get to that, related to this, there will almost definitely be conversion questions. I would say high likelihood of converting between a hexadecimal number and an octal number, that kind of stuff. I like putting conversion questions like that in almost all of my exams and all my classes. In a class like this, it would probably be a more difficult conversion question, like not convert this number into decimal or decimal into this number, but maybe convert a base into another base. So like I just gave the example, maybe a hexadecimal number into octal. Or even go to a base that doesn't necessarily have a name. So I might say convert this number from base 17 into base 22. Something like that. All right, they're all the same. If you understand one, you should understand them all, because it's not like you have to memorize different bases, but that'll show me that you understand that conversion process. Okay, so guaranteed 1 conversion question, probably a couple on an exam, on this exam. All right, so then we get into the assembly language. So we're going to talk about this at a couple of different levels here. So to begin with, we were talking about hardware registers, so we want to understand the purpose of those hardware registers. We want to understand, this was our talking about Apple's new chip. I won't ask you anything about that. That was the architecture related to the new iPhone. They have a quad-core chip, but 2 of the cores are low-power cores. Interesting, but won't be on the exam. That the ELF is an executable linking format for building your assembly programs into an executable on like Linux, something like that. Won't be on the exam. That won't be on the exam. Okay, so back to the registers. I would probably, so we would talk, the registers I would talk about in here are going to be the ones dealing with the 8086 processor that we've been working with. So the EAX, EBX, those started with 286, so those won't be on the exam. But I would expect that you would understand that AX, BX, CX, those guys are all 16-bit registers that each have a high and a low. All right, so if I gave you a scenario where I had a value in AX, and then I did a add AH comma AL, what the result would be and what it would impact. So add always puts the result in the destination register, the left one, right? So if I had a value inside of AX, its high 8 bits would be added. It has a high 8 bits and a low 8 bits, right? And then if I add the high 8 bits to the low 8 bits, storing the result back in the high 8 bits, I would want to see what the register would be in the end. Okay, so make sure you understand working with general purpose registers, doing addition, that kind of stuff, and where the value ultimately gets stored. Make sense?
So should we know, like, these registers and their bit values?
You should definitely know that AX, BX, CX, DX are all 16-bit registers that also have a high and low that are each 8 bits. That should be something you know. The EAX stuff doesn't exist in our 8086 world. I probably wouldn't expect you to, deal with anything with like the SI registers or anything, the other general purpose registers for index pointers and that kind of stuff. But I think the big four, we should all know those, right? They're all 16-bit registers. You just count through the alphabet, right? A, B, C, D. We got that. We got the first four letters of the alphabet. Everybody has those. Throw an X at the end of each of those. Those are your 16-bit registers. And then each one has a high and a low. So be able to work within those. On the exam, a significantly higher precedence on registers and math than on flags. All right, so there could be like a side question of like, the zero flag, for example. So if we just throw a possible question out there, I might ask a question like, when would the zero flag be set? Give me an example of when the zero flag would be set. Okay, so one example could be when you have a arithmetic operation where the result was zero. Zero flag gets set, right? So you can say that's an arithmetic operation. You can say a compare operation. The book has talked about compares, right? I don't know. Have we done compares in here in actual class? We at least talked about it with the different jumps, I think, right? Yeah. So, the idea would be is when you compare two values, if they are equal to each other, because it's actually doing a subtraction, zero flag would get set. Yep, that kind of stuff. So I might ask you to give me an example when the zero flag would get set. Similarly, give me an example where the carry flag would get set. When would a carry flag get set? If I asked you on an exam to give me an example, a concrete example of when the carry flag would get set, what could you do? Okay, so if I said write some assembly code that ultimately set the carry flag, how would you do it? Give me a specific example.
Using assembly code?
Sure.
Okay, just you say add an 8-bit number from AH to an 8-bit number from AL. Both of them have a 1 in the first thing, so when you add them up, it's going to be a 0 across the board, and then a 1 in the carry flag.
Okay, so if we had two 8-bit numbers, even if it was 1 followed by 7 zeros and another 1 followed by 7 zeros, we add those two together, we're going to have a carry because the sum of those two numbers is too big to fit in an 8-bit, right? Because the destination register would be 8-bit. So carry flag would mean that we've exceeded the capacity of that register. Okay, so relative to that, I could ask a question like, what is the largest decimal value that would fit inside of a 8-bit or a 16-bit register? Or I could ask, what is the largest value that would fit in there? And you can give it to me in decimal, octal, hex. So 8-bit register, what's the largest hex value that can fit in there? Should be real easy. Largest hex value that will fit in an 8-bit register. FF, yep, FF. Right? Yes. That's right. Give you a little wink.
He did?
Yeah, oh yeah, I was watching it.
He knows he's cool, and he just wanted me to know that.
Yeah, he wanted you to be aware. Yeah, because when I talk about 4 bits, what's a synonym for 4 bits? When I'm dealing with a 4-bit value, that's a what? Nibble. Niblet. I'd probably take it. It's kind of the cute. That's a cutesy name.
That's a single. That's a single niblet or a nibble.
I don't think niblet's anything. but yeah, so it's a nibble, right? So 4-bit value is a nibble, which also happens to be what we need to represent a hexadecimal value, right? 0 to 15 is what will fit in a nibble, or 0 to F. That's 4 bits, so 8 bits would be FF, largest value. Make sense? All right. So understand those kind of concepts. What's the maximum, minimum value that will fit inside of a 8-bit register? A fun question that just came to mind, so it potentially could come to mind on an exam, would be, what's the smallest value that could fit in an 8-bit register?
The smallest.
Smallest value.
Negative, whatever.
Yeah, 128. Because the 0 is the positive side. So that's why we lose 1 bit. So it would be negative 128 on the negative side. If I told you to do that in hex, how would you give me the hexadecimal value of negative 128? Just take me through the process. Yeah, you don't have to come up with a number. Just take me through the process of the hexadecimal value of 128. So binary negative 128 is what? A 1 followed by, what's the binary version of 128? Yeah, all ones, right? All ones. Okay. Wait a minute. That's only, all ones would be 7 bits. Well, but we have 8 bits for a binary number.
So 0, 7 ones.
Okay? So 7 ones,
Would be all ones.
all ones. Okay, so then you'd have to encode it in 2's complement, right? That gets you your negative 128. So you'll take 128, turn it into negative 128 by encoding it in 2's complement, and then you can convert that to hex. It would be fair game for me to say, give me the answer in a specific value, a specific base, because I want you to do a lot of conversion stuff because those are my favorite, right? So expect that. I like conversion questions. I like competence relative to converting numbers. So I would expect that you should be able to do a lot of that. I think it'll do you a great service if you practice conversion. There will probably be 1 or 2 direct convert questions, and then several indirect conversion will help you questions. Make sense? All right, so as far as registers go, I think the big 4 are the most important: AX, BX, CX, DX, and then understanding the high and low of those. I will likely give you some assembly language examples and say, what is the result of this? Working with those 4 registers. I could also ask a question relative to the flags, the carry flags. 0 flag and carry flag would probably be the only 2. They're the only ones we've really kind of talked about. But like I said before, those would be pretty low priority for me. If I asked a carry question, it would probably be 1 question, where I can pretty much promise you multiple questions dealing with the registers themselves. Okay, there'll probably be a couple of questions where I ask you to write assembly code, and then a couple of questions where I give you some assembly code and ask you to tell me what the result of this is, or what's stored in BX at the end of this, these 5 lines of code or something like that. Make sense? All right, so there's our picture. So understand that your 16-bit general purpose registers are divided into a high and a low. Okay. Understand the concept of base addresses. All right, so we just recently started talking about arrays in here, right? So arrays would be fair game on the exam in terms of arrays using assembly, but my gut feeling is if I asked an array question, it would probably be one that asking you to read code and tell me what the result of it is, as opposed to write it. Because we don't have the convenience, loops and stuff like that starts taking up more screen space or paper space than I want to take up. But understand this concept of base addresses, where we have stored somewhere the pointer to the address of something in memory, and then we use that address to walk an offset from there to get to another location. Make sense? All right, so understand base address. Move instruction. All right, so we looked at some of the different ways this guy can work. I wouldn't ask you to memorize this specifically. But if there was one thing that you should at least know, is that you can't move a variable into a variable directly. Probably wouldn't ask the question, but if I did ask a question related to the syntax of move, it would be you can't move var into var. You have to move var into a register and then that register into a var. Okay, because vars are dealing with system memory, which is slow, and they both require lookups. So that's a pretty complex, slow instruction to have to execute in order to look up two different values and move stuff from one to the other, especially when you consider that you need an intermediate location anyways in order to accomplish that. All right. So understand the concept of the move instruction because you're going to have to be able to read code related to it. That's carry flag stuff. And instruction. So if we and two numbers in assembly, what happens? What's the result? How does an and work in assembly? This goes back to something we glossed over in when we talk about this in like 250. Go ahead.
Does it compare every bit to the two numbers you're comparing?
Yeah, so it's bitwise, right? So if we have two 8-bit numbers and we do an and on those, the result is an 8-bit number. Okay, and the result is an 8-bit number based on anding each related bit to each other. So a 1 and a 1 is a 1 and a 0 is a 0 and a 1 is a 0 and a 0 is a 0. Make sense? So it's a bitwise and, so it's an arithmetic operation. Okay? Same thing with ORs. ORs are bitwise as well. Okay, what about XOR? What's the truth table for an XOR? A 1 XOR 1 is going to be a what? 0. A 1 XOR 0 is a 1. A 0 XOR 1 is a 1. A 0 XOR 0 is a 0. So XOR, exclusive OR, says one or the other, but not both. So a 1 XOR 1 is actually false. That's a 0, because you can't have two 1s. If it was an OR, 1 or 1 is a 1. That's the differentiating factor between ORs and XORs. Okay? Let's see. This is something we talked about pretty early in the semester just to kind of give us an idea of computing evolution. I probably won't ask a question on it, but still an interesting thing to say out loud again. So if cars had changed the same rate as our digital circuits have changed, we would be able to drive from New York to London in 1 second for the cost of a penny. So wouldn't that be cool? I mean, that's pretty much teleportation, right? But just moving really fast. Better have barf bags on there probably. All right, I think we are. That's conversion stuff. There's 2's complement. All right, so here is our examples, our alternatives to 2's complement. So one of the alternatives was sign and magnitude. All right, so this is where we use the most significant bit, the bit farthest from the left, to represent sign, negative value versus a positive value. And here's that idea where we have a -0 and a +0. So 2 zeros in that model. So that's the weakness of that. Whereas the 2's complement, we have a -4 up to a +3. So that's where we get our extra value on the negative side. But we only have 1 0 represented. Make sense? Okay. So then we would talk about, well, probably procedures in assembly would be a helpful topic. I might show you some short code that has 2 procedures back to back and ask you what the output of this program might be. And if we don't have a return statement, what happens? If we get to the end of our main procedure and we don't have a return, what does the assembler keep doing? It just keeps going linearly, right? So labels, which is effectively our procedure headers, are just labels. they aren't segregating the different parts of the program. So when I'm walking through line by line by line, and this, we have a call command. So the call command, which calls a procedure, what does that do? What's the side effect of the call procedure? Okay, it jumps to a different place in our code. What else?
The previous position
Yep.
is popped on the top of the stack.
Yep, so it pushes onto the stack its mechanism for returning, right? For getting back to where it left off. All right, and that mechanism is an offset based off of the base address of the code segment, right? All right, where's the code segment stored? If I were to ask a question like that. The address of the code segment, the base address of the code segment is stored in what register? All right, it's neither of those. Here's the hint. Code segment is 2 words, each starting with a letter. It's in CS, code segment. Where is the base address of the data segment? DS. Makes some sense why they named them those. All right, so those would be fair game questions. Like I said, I wouldn't ask you to memorize a lot of the other registers, but where is the base address of the code segment? If I was looking for a quick throwaway question, you should probably know that. All right, so CS, DS, those would be the 2 that are meaningful. Also, I'm sure we'll scroll down to it here in a few minutes, but since it's fresh in my mind now, also how the data segment is organized, kind of treated like an array, based off of a base address. So each variable defined in our data segment has an address that is based on the offset of that variable relative to the base address of our data segment. How do we get that offset? If I have 2 variables in the data segment, I have var1 and var2. How do I find out the offset of var2 relative to the base address of DS? Base address of our data segment. Okay, so we have a command called offset, which gives us, so offset has a variable right after that, and that gives us not the value of that variable, but instead it gives us the position relative to the data segment's base address of that variable. Gives us the offset of it. Make sense? So make sure you understand how that works as well. Okay, that goes back to the whole base address stuff, understanding base addresses and offsets, and that's kind of a 1-2 punch for working with memory. All right, something we learned back when you had 200 with arrays, how arrays work. Now we're seeing it in practice at the computer organization level. Everything is based on addresses and relative offsets from some base address. We see that even at the 8086 level. We have a couple of registers that remember where certain parts of our program start, right? So we kind of know how memory is divided up. So back to procedures. We use the call instruction to start a procedure, and the call instruction has a side effect of pushing onto the stack the base, well, not the base address, the offset from the base address of CS, where we need to return when the procedure ends. So when we have a return at the end of a procedure, that return effectively says, pop the current value off the top of the stack and go there and continue fetching instructions from that point. Make sense? All right. So it's important we understand that side effect, because if you're going to use the stack, so this goes back to when we were talking about procedures and utilizing the stack for parameters potentially versus utilizing registers, that you have to play that game that the top of the stack is important, right? That your first parameter won't be at the top of the stack. What's at the top of the stack after a procedure call is going to be the return address. So you need to get that off the stack, preserve it, then grab your variables, your parameters, then push that guy back onto the stack so you can get back where you came from. Okay, so it relies on you understanding how stack manipulation works relative to procedure calls. So here's the stack stuff, pros, extra memory for storing stuff. So stacks are, I would say stack functionality in general, like we just talked about, will definitely be on the exam at some level. Whether I ask you directly about the stack like this is maybe more of a 50-50 thing. So understanding the mechanics of working with the stack pushes and pops and what each of those do. Pros and cons. So pro of it gives us extra memory stuff, extra places to put stuff because we have a limited number of named registers, but it becomes an anonymous type thing where we aren't able to easily get, easily distinguish between what's on the stack. They're just a bunch of values. So we have to kind of juggle what's on the top of the stack right now in our mind to make sure that our logic doesn't get broken. And you can imagine that those could also be difficult problems to debug, if you have some stack confusion. So that's where variables come in. Because variables give us a way to name our values that we need to store at the side effect of speed, right? Although we imagine that the stack is going to be slower than a register, but potentially, depending on the architecture, faster than system memory. Because some architectures have a stack built into the CPU. It's kind of like cache memory. Others rely on system memory for accomplishing the stack. Okay, so there's our push and pop. Peak is, so this is more of a interacting with stacks in general, the stack data structure. Push and pop are our stack methods that are built in. Peak is a convenience method for stacks. Often lets you just look at the top of the stack. It's not available in 8086 assembly, but just for completeness, dealing with stacks in general, we can implement peak by popping off the stack, looking at it, and then pushing it back onto the stack. That's effectively the same thing, right? Okay, so here's our wraparound logic for a stack. So when we look at a stack in the, really any stack, so if we're taking this in like a CSC300 direction, where we start off looking at stacks implemented as arrays, is kind of CSC300 has us hobble towards this idea of linear linked data structures, and then we do nonlinear linked data structures. The idea is that those guys can be arbitrary in size, but we start off by trying to implement those guys as arrays. So if we have a stack implemented as an array, that means we have a fixed stack size, which should match up to the idea of computer architecture, right? So we have an amount of memory that's reserved for stack space, and that's fixed, which means that our stack is finite. Okay, it's a decision that we make before we initially launch the program. Sometimes the decision is made for us by the architecture itself. More modern architectures allow us to designate the stack size. So unimportant, that won't be a question I'll ask. But the important thing for us to know is that stack size is fixed at runtime. Okay, which means that we do not have an infinite stack, which means as we are adding things to the stack, we potentially lose stuff. So when we do our wraparound logic, we add something to the current offset plus 1 mod the size of the stack. So bucket 0, bucket 1, bucket 2, bucket, if I get to bucket 8, this is a bucket 8 here we think should actually wrap back around here, right? So if I try to index bucket 8 of the stack, or bucket 8 of an array implementation, 8 mod 8 is 0. 8 goes into 8 one time with no remainder. So that is what wraps it back up here. Bucket 9, 8 goes into 9 one time with remainder of 1. Bucket 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Get the logic? Okay, so modulus allows us to do wraparound logic for our stack. Not something we necessarily have to remember. I'm going to call it a 10% chance I might ask something like that. If I did, I would maybe give you something that looks like this and ask what bucket does bucket 31 relate to. Okay, so, or what memory address is bucket 31? So how many times does 8 go into 31? Okay, so 4 times 8 is 32. Remainder 1. Okay, so it's actually memory address 104. Right? So bucket 31 means I did take 31, I divide it by 8, I get 4, remainder 1. What's 8 times 4? That's 8 times 3. What's 8 times 4?
32.
Okay, so 8 does not go into 31. Okay, it goes in 3 times with remainder what?
Remainder 1. And I was like, what? It's remainder 7.
Remainder 7. So that's bucket 0, 1, 2, 3, 4, 5, 6, 7. Memory address 128. Okay, so if I ask you what's at bucket 31, you would take 31, you would divide it by 8, record the remainder, which is 7, because 8 does not go into 31 4 total times. It almost does. That's 32. Goes in 3 times with a remainder of 7 to get to the 31. All right, so that's where the wraparound logic comes from. All right, conversion questions, definitely. The concept of the system call API related to DOS, so there'll very likely be something related to this, whether it's me giving you the list of system calls and having you write some code that does something, print a character on the screen or something like that, or more at the high level, asking kind of, what's the purpose of the DOS API? So as an example, what is the purpose of the DOS API? Why does it exist? Just cause? Go ahead.
Using the tools that the operating system provides to us.
Okay. So operating systems kind of have a job to do, right? So they provide they provide a mechanism for us to interact with our hardware. They make life easier for us, and it's done through a bunch of software-based magic tricks, right? So operating system has a bunch of conveniences built into it for working with file systems and working with memory and working with hard drives and all sorts of stuff like that. Working with user input. So it has stuff like that built into it. So instead of us having to reinvent the wheel, we can utilize the operating system's built-in functionality from within our assembly program and say, let's let the operating system handle this logic. I want to read something in from the user, so I'm going to stage everything here, then call upon DOS to go and do its thing. And then it's going to put my answer, in a place where I can find it in a few minutes, and then I can move on with life. Make sense? So that DOS API is there for us to be able to accurately interact with the operating system at the assembly language level. So we can rely on the operating system to do some heavy lifting for us so we don't have to do it ourselves. It's kind of the purpose of an operating system, right? From a programmer's perspective. From a user's perspective, the operating system allows us to actually use our computer so we're not interacting directly with hardware and wires and stuff. But from a programmer's perspective, we want to be able to rely on that operating system to allow us to do some stuff for convenience, right? Reading stuff in from the user, writing stuff out to the user, that would be complicated stuff. Because now, if we didn't have the operating system to do that, what would it take to write something out to the user? To put hello world on the screen, what would it take without an operating system? What would you imagine?
Zeros and ones. You don't have any
Zeros and ones to what? Where are you seeing the hello world? You seeing it on the monitor?
I mean, if you're saying there's no operating system, then you'd have to make it yourself, basically.
Okay, so I have a monitor sitting in front of me, and I want hello world to show up on that monitor. How do you imagine that might work? Feed some electrical signals into the monitor. Certain pixels light up, other pixels don't light up, that kind of stuff. So, I mean, it's a lot of manual work, right? Okay, so It's actually pretty impressive what operating systems do for us. Even old, simple operating systems like DOS, we can appreciate the heavy the heavy lifting it does for us, so that we don't have to interact with the monitor directly. We don't have to interact with the keyboard directly. More modernly, operating systems then have modular device drivers, right? So we don't have to interact with any device directly. We interact with the devices through the driver API provided to us by the operating system, so that we can tell our brand new, latest, greatest USB device XYZ to do what it's supposed to do, whether it's some new scanner or something like that that does something fancy or whatever. Okay, so system calls, important, allow us to leverage the operating system. Okay, so $ terminated strings will definitely make a appearance on the exam. I could have a code example that uses a different type of termination or does something with $ termination strings. I could see there being a coding question dealing with $ terminated strings, but probably not one that has you manipulate them or anything. It's too much work for the time frame we have. I would expect you to understand that concept of where that $ is where the string terminates, but writing that in a short period of time, just because of the nature of assembly, is problematic. So I probably wouldn't ask you to do string manipulation stuff in assembly yourself, but you should understand the concept, because this is actually kind of a picture of our data segment, which we referenced a few minutes ago, right? So our data segment kind of looks like a big array where we have two variables here. So we have a base address of our data segment, which looks like it's at 100. So that's the base address stored in DS. And the offset of param1 would be 0. It's right at the beginning of DS, although we've seen that that's not entirely true. There's some stuff stored at the beginning of the data segment to kind of tell us about the contents of the data segment. But for simple math, we're going to say the offset of param1 is at 0. Its true offset is at offset of param1, whatever that value is. So that gets us here. We go until we hit the $. That's the end of that guy. The offset of param2, I have at 104. Again, its actual value is going to be whatever offset of param2 returns. So that's our collection of variables inside of our data segment, which is effectively a variable environment. Okay? So you should understand the data segment. You should, so right here we moved into DX, the offset of param1, which the offset of param1 by my example here is going to be 0, bucket 0, which is base address of DS, which is 100 plus 0, which is 100. So that's what will be stored inside of DX. And then we'll move into AH, the 9. So this is the display crop to the screen code. So this is display a character to the screen DOS API call, which, like I said, you don't have to memorize. I'll give it to you if I want you to use it on the exam. And then what's this line right here do? Interrupts the program and calls who? Calls DOS, calls the operating system. But specifically, this calls DOS because there are different interrupts. So for instance, the interrupt for Linux is ADH. So it's a different interrupt call because the operating system is, so when we interrupt the CPU, it knows who to call. And the operating system itself, when it loads into memory, it puts itself into a position where it's awaiting this. Okay, so this specifically calls DOS. But if I were to ask this on the exam, you could just say this calls the operating system. It's this is the go command for after you set up a API call. There's our terminating stuff. That's our array stuff. All right, so this was our studying of the $ terminated strings in Java. Okay. All right, questions? Anything you want me to review or anything you want to clarify, whether I deem it to be important or unimportant? Going once. All right. I will see everybody on Thursday.